Hello everyone. In this presentation we were discussing about the metal casting, and in the previous video we have discussed about the casting terminology and casting definition. In this video we are going to discuss about the pattern and its allowances. Okay, so let's start. Patterns are basically the shape of the casting that is required, and accordingly we shape the patterns. Okay, or in other words we can say that it's basically a replica of the metal casting. Okay, or metal casting means whatever the shape of the required, it is basically a replica of that. Okay, the same like what the casting is required. Okay, now these patterns are made up of the wood, plastic, metal, sometimes it is made up of the wax or mercury. It depends on the which process, metal casting process we are using and what are the environmental conditions. Okay, but maximum casting occurs at a atmospheric temperature, so the patterns of the wood and plastic is efficient. If the shape is very simple then we can make this patterns into the carpentry shops by the wood, and if these shape is complex, then nowadays we are using 3D printing models as well, okay, as a pattern. So and the selection of these patterns is depend on the what are the shape and size of the casting, what is the dimensional accuracy required, how much quantity we are producing from that, and which is the molding process or casting process we are using. Okay, so from this figure we can understand that this is basically the pattern. Okay, and we can say that this is basically the shape that is required. Okay, that we will get at the end of from the casting. Okay, and this is the molding set that we are preparing accordingly. Okay, and here we are using a parting line. Okay, so below that parting line there is a drag, above that there is a cope. Okay, so cope basically is required as we are completely fixing this pattern inside this drag, so that's why I have not mentioned here the cope part. Okay, but just assume that when it will fill, we'll keep this cope part above to the sand mold. Okay, so this is basically the pattern or the shape required, and this is basically the sand mold. Okay, next is pattern allowances. There are different types of allowances like shrinkage or contraction, draft or taper, machining or finish allowance, distortion or camber allowance, wrapping allowance. Apart from it, if you will study the number of books, then you will get to know that there are different allowances are also available, means with the different name. Okay, but anyhow all these allowances are some related with each other. Okay, that will also I will tell you in upcoming videos. Okay, so in this video we are going to discuss about the shrinkage allowances. Okay, so shrinkage allowance or contraction allowance occurs when this molten material is become a solid part. Okay, as we know that when we melt a material, basically a material existed in three phases: liquid phase, solidification or phase transition, and the solid phase. Okay, so with the very I'm using this graph, like on x-axis there is a temperature, on y-axis, sorry, on x-axis there is a time, and on y-axis there is a temperature. Okay, so initially if we are talking about iron carbon diagram, then at 15 to 34 degrees centigrade the material is melted, okay, or above it. So here I am using this temperature, that this material is completely melted, and we are filling this mold cavity. Okay, so how this mold cavity, how the phase transition with respect to the time and with respect to temperature is occurs, so we are going to look into it. So here it is basically the molten material. Okay, once it is filled inside the mold cavity, it will get it will be cool, and as the continuously temperature decreases with respect to time, some part of it become semi-solid, or there is a formation of the dendrites. Okay, because it is completely liquid, and with respect to temperature the liquid try to become a solid phase. Okay, so basically it is reaching from liquid phase to the semi-solid. Okay, and that phase we are calling it as a the temperature is solidification temperature, and solidification phase we can say, or phase transition we are calling it. Okay, so once the formation of this dendrites started, okay, and whole there is a formation of the dendrites inside this liquid material. Okay, so it will take also some time with okay, so this is basically the phase transition. And when there is a complete formation of the dendrites, so this material will come contract. Okay, these dendrites become contracted with each other, so the volume of the solid become less. Okay, and we know that whatever the material is there, if there is a liquid form of the same material, then the volume of that liquid is greater than whatever it is in solid form. Okay, so from here, from liquid to the, when there is a formation of the semi solid phases or dendrites, we call it as a, the allowances there is, we call it as a liquid shrinkage. Okay, and there is a, when all the dendrites form at the solidification temperature, we call it as a solidification shrinkage. Okay, when this dendrite, all these dendrites become contracted and it will reach to the room temperature, so we call this phase as a solid contraction. Okay, next is this is a very wonderful concept that you have to keep in mind for the numerical problem as well. Okay, that and also I have discussed in the previous video that whatever the material that is coming out from the riser, okay, so that is in the liquid form or semi solid form. Okay, because whatever the liquid which is coming out from the riser initially, so that is filled initially inside the mold cavity. Okay, so when whatever the time is required to fill the mold cavity, that has been already taken, and up to that time this material is already cooled. So whatever the material that is coming out from the riser, that is in the liquid form or semi solid form, so that is affiliated with the liquid shrinkage or the solidification shrinkage. Okay, next is, if we are talking about the casting, then this casting is basically, that is a mold cavity. So whatever the material is there, if it is a liquid, it is coming out, but it is not coming out. Whatever the material is there, that is in the solidification form, or because that will be only the our final shape, so that will become a solid. Okay, so the shrink allowances that is affiliated with that is shrinkage, solid contraction, and solidification shrinkage. Okay, in oblique of this casting I have written pattern, because when you will go to go to discuss about the numerical problems, we will see that after all why we are using these allowances. Okay, and how we will use these allowances. So basically these allowances, whatever the allowances given to a particular material, that is added to the pattern. Okay, this will also see in problems. Okay, so rate of contraction for the different materials, like here I have taken a two example, that is grey cast iron and cast iron. If we will talk about the aluminium, bismuth, plain carbon steel, cast iron, all these material have a different rate of contraction. Okay, so because all have a different melting temperature, so the rate of contraction is also be different. Okay, the cooling rate basically we can say. So here I am taking two example, cast iron and grey cast iron. Okay, now as per the, if we are talking about a volume, then volume is basically a three-dimensional body. Okay, so here I am not in this data, it's basically the dimensional change in, it's a dimensional change, it's not a volumetric change. Okay, whatever I have written here, like when there is a grey, we are talking about a grey cast iron, then if there is a like dimensions are up to 2 feet, then rate of contraction is 0.125 inches per feet. Okay, then if this dimensional is increases from 2 feet to 4 feet, then the rate of contraction is 0.105 inch per feet, that is reduces what we were using previously. Okay, and if it is above 2 feet, then this rate of contraction is also decreases and it is become 0.083 inch per feet. Okay, so this is continuously reduction, means if you are increasing the dimension, okay, then the rate of contraction is decreases. Also this please keep in mind. Okay, so similarly for the cast iron, there will, because the material is different, so rate of contraction will also be different. Okay, next is a numerical problem. So how this allowances is basically affiliated with the pattern, so that we are going to look into this problem. So the problem is the casting shown in is to be made in gray cast iron using a wooden pattern. Okay, so the final casting will be of gray cast iron, but we are using a wooden pattern here. Okay, assuming only shrinkage allowance, so we have to calculate the dimension of the pattern, and all the dimensions are given here is in inches. So this is basically the figure that is given to you for the final casting. Please keep in mind this is a final casting, so we have to design the pattern for this. Okay, now this final casting is basically have the dimension like length is 18 inch, width is 14 inch, this thickness is 8 inch, and the inside there is a hollow cavity throughout this thickness, so that is a diameter of 6 inches. Okay, now first of all, that what we have to do is we have to calculate the dimensions for the pattern. So like here, like this shape only we have to prepare. What is pattern? Pattern is basically the replica of the object or replica of the metal casting. Okay, so this is the casting. Okay, and we have to prepare the same shape, but there will be the dimension changes. Okay, why this dimension changes? Because rate of contraction is there. Okay, so now first of all what we have to do is, in the previous slide for the gray cast iron, we know that if there is a up to 2 foot, then there will be the rate of contraction is different. In between up to 2 feet to 4 feet, the rate of contraction will be different. So first of all we have to find out that in feet basically what these dimensions are. Okay, so first there is a conversion that 1 feet is equals to 12 inches. Okay, so these dimensions are given in inches. So first we are converting it into the feet. Okay, and we'll see that how this feet range is belongs to, whether it is less than 2 feet, in between 2 to 4 feet, or above the 4 feet. Okay, so we'll take the rate of contraction accordingly. Fine. Now like first is 18 inches, like this is the length, that is 18 inches, we are converting into feet, so that is divided by 12, so we'll get the 1.5 feet. Okay, width is 14 inches by 12, that is 1.167 feet in. Okay, and similarly this thickness is 8 inch by 12, that is 0.67 feet. Okay, and the diameter of this cavity is 6 inches by 12, that is 0.50 feet. Now if you will see the dimensions in feet, all these 4 dimensions, then length is 1.5 feet, the width is 1.167 feet, the thickness is 0.67 feet, and the diameter of that is 0.50 feet. All these dimensions are lesser than 2 feet. Okay, so we have to take the rate of contraction will be 0.125 inch per feet. Okay, now one more thing is that like if the dimensions are less than 2 feet, then we have to take this rate of contraction, but it doesn't mean that for all the dimensions, for all the individual dimensions we have to take this as 0.125. no, this is for 2 feet, but all these dimensions are different. Okay, so the rate of contraction or rate of contraction in these dimensions will also be different, but the rate is same, but the final changes will be different because the length of size of this dimension is different. Okay, like length is different, width is different, thickness is different. Okay, so how this will change? Like if there is a 18 inches, then this rate of contraction is 0.125 inch per feet. Okay, so we are converting into the inches, so we'll take this feet is equals to 12 inches, so 0.125 inch by 12, so that will give you the inches. Okay, so 18 into 0.125 by 12, so that is equals to 0.1875 inches. Okay, now this is basically the contraction. Okay, means if you have to prepare a casting of 18 inches, then you have to take the dimension of the pattern 18.1875. okay. Similarly, for the 14 inches, allowances will be equals to 14 into 0.125 by 12, that is equals to 0.1458. So the final dimension of the pattern will be equals to for the width is equals to 14.1458. okay. Next is the 8 inches. 8 inches allowances will be equals to 8 into 0.125 by 12, so 0.083. okay. Next is the diameter of that hole, that is 6 inch and 6 into 0.125 by 12, that is 0.0625. Now these three are basically the outer dimension of the body, okay, and this is basically the internal. Internal means we are in between, we are making a hollow cavity. So now here we are just considering this example that this is basically the rectangular and inside there is a hole, okay. So the contraction means whatever the material inside this portion, solid portion, that will be contracted with each other, okay. So that's on, because of that only the volume is become less. So when this material is contracted with each other, whatever the shape is there, this will not move out inside, this will move outside, means it will contract towards the solid material, okay. So if we are, whatever the dimensions we are taking, like if we'll take more dimensions, okay, like we are saying that 6.0625 dimension we are taking, okay, then it will not become less, it will become more, it will increases. So the final dimension will be more than of this, for this hole the final dimension will be more than 0.0625. so what we have to do, we have to reduce this dimension, okay. So final dimension for this hole will be equals to 6 minus 0.625, okay. So this will be the final dimension. Length of the pattern will be 18.1875, width is 14.1458, thickness is 8.083, and the diameter of that will be equals to 5.9375, okay. Next, this is also a wonderful problem that has been asked in GATE 2011. A cubic casting of 50 mm side undergoes volumetric solid shrinkage and volumetric solid contraction of 4% and 6% respectively. There is no riser is used. Assume uniform cooling in all directions. The side of the cube after solidification or contraction is, okay. Now there is a casting is basically we are casting a cube here, okay, and the side of that cube is 50 mm, okay. Now whatever we have discussed previously, that rate of contraction, that is in particular dimension, okay, particular dimension, that rate of contraction is 0.125 inches per feet. But here it is given that the volumetric means the volume is changing, okay. So the volume is changing. If volumetric shrinkage, volumetric solidification shrinkage rate is 4% and volumetric solid contraction is 6%, okay, and there is no riser is used. This is very, very important in this question, okay, because if there is no riser is using, then what are the allowances that is affiliated, what are the shrinkage allowances that is affiliated with the riser is liquid shrinkage and solidification shrinkage, means we do not have to use that one, okay. And by the way, that liquid shrinkage is also not given in this question, okay. Now what we have to do is, we have to find out the side of that final volume, okay, final whatever the casting we are using. So we have to find out the side of that cube, okay. Now actually there is no direct formula, but just we have to, with the help of concept, we have to find out these values, okay. Now possibilities, the side of the cube that we have to find out. So what we are going to do is, first we are finding out that what is the volume of that solidified casting, okay. So that will be equals to the whatever the actual volume of this casting, and into what are the rates, okay. like if we'll find out what are the rates are there. So means if there is a, we are using that solidification shrinkage, okay, then if we'll use 4%, then this much amount has been reduced, 4% has been reduced from the solidification shrinkage, and 6% is reduced while there is a solid contraction. But what is amount is remaining, that is important. Okay, what amount is remaining, that the dimension we have to find out for that casting. Okay, so for that volume I'm using a formula, that this is not a permanent formula, but this is through the concept only, that volume after the solidification, that will be equals to volume of the casting into 1 minus solidification shrinkage volumetric, and into 1 minus volumetric solid contraction. Okay, plus why I'm writing this formula, because like just to think about that, if I will not write 1 minus solidification shrinkage, then I can, if I will write simply that solidification shrinkage or here solid contraction, then this much volume you will get, that how much has been contracted. Okay, whatever the material is there that has been contracted, so that we will find out. But we do not want that. How much is remaining, how much volume of the casting is remaining, that we have to find out. That's what I'm using 1 minus here also and here also. Okay, so the volume of after solidification will be equals to volume of the casting into this. Okay, so I'm using a side of the solidified casting is B, and for the casting, that is 50, that is A. Okay, remaining are same. Okay, so when you'll put these values, like A is equals to 50 and 1 minus solidification, that is 0.044%, and this is 0.06. So we'll get this 50 cube into 0.96 into 0.94, and when you will calculate it, you will get the value of B, that is side after the solidification or contraction. Okay, so this will be equals to 48.3173 mm. Okay, so this is the first answer. Okay, A. Next is also a gate problem that has been asked in GATE 2008. So while cooling, a cubical casting of side that is 40 mm undergoes 3%, 4% and 5%. First, that is this 3% is volume shrinkage. Okay, this is also, like in this problem is also given that volumetric shrinkage is there. Okay, in liquid state it is 3%, in phase transition, so solidification shrinkage we can say, it is 4%, and solid state, that is solid contraction, we can say it's a 5%. Okay, so the volume of metal compensated from the riser. Okay, so now here the important is riser, we have to think about the riser. Okay, and one more thing is it's not asking the volume of the metal compensated from the riser, is basically it's not asking that how much volume, but how whatever the rate of contraction or rate of these allowances is given to you, how much percentage is affiliated with the riser. So that we have already discussed this concept, that riser is affiliated with the liquid shrinkage or the solidification shrinkage. Okay, so just you have to see that what is the value of this shrinkage allowance. Okay, so for the liquid it is 3%, for the solidification shrinkage is 4%. Okay, so that is 3 plus 4, that is 7%. So answer is B. Okay, here it's not asking that what is the volume of that riser and all these things, but just asking that how much percentage of the rate is affiliated with this, rate of contraction is affiliated with the riser. Okay, next is also a GATE problem that is asked in 2001. The shrinkage allowance on pattern is provided to compensate for shrinkage when these are the some, like what we have discussed in the first figure graph, that is like liquid shrinkage, solidification shrinkage, and this solid contraction. Okay, so here in this problem, please see, look at here that shrinkage allowances on pattern. On pattern means like it is talking about the casting. Okay, because whatever the contraction is there, that will be in casting, so that is affiliate, that will affect the dimension of the pattern. Okay, so here what are the allowances, what are the shrinkage allowances that is affiliated with the casting? Solidification shrinkage or solid contraction. Okay, so first option, the temperature of liquid metal drops from pouring to the freezing temperature, so that is basically the liquid shrinkage, that is not affiliated with this, so this is not the answer. The metal changes from liquid to solid at freezing point. Liquid to solid means only there is a shrinkage allowances. Okay, liquid to shrinkage, it means why liquid to solid state but at freezing temperature, so that is only solidification shrinkage. Okay, now you'll see first this D option, the temperature of metal drops from pouring room temperature, means from molten material to the room temperature. So all the shrinkage allowances, liquid, solidification, solid contraction, is all these are affiliated with this, but here is asking about only for the pattern or the casting. Okay, so just see, look at C option, the temperature of solid phase drops from freezing to the room temperature. So at freezing temperature there is a solidification shrinkage, at room temperature there is a solid contraction, so the correct answer is C. Okay, in this video we are stopping here because it is going beyond the limit. Okay, in next videos we will discuss about the other allowances. Okay, so thank you so much guys.